Welcome back to our session. Now we will focus our attention on circuit problems, but of importance to us is also to try and understand how we approach these circuit problems, but we'll try and use the EMF equation to see how exactly we apply it in as far as circuit problems are concerned. Right. So we also need to remind ourselves that the Ohms law becomes very, very important, and also because it's a circuit, we could either have a series or parallel, or a combination of series and parallel circuit. Right. Okay. So questions may give EMF. So EMF might be given, but then say internal resistance can be ignored or is negligible. So in most cases, or in some cases, if we ignore internal resistance, we'll know that the EMF will equals to external voltage. But however, if we look at it in terms of the EMF in the circuit, which does not change, we are saying that the current outside the battery, which is the main or the total current, is actually the same as inside the battery. All right. Okay. Now, given the EMF and the total current, we are also able to find the internal resistance of a battery. Now, in short, what we are saying, in as far as internal resistance is concerned, in a circuit, you can either be given internal resistance or not given. Either of the two, it's not a trace mesh. As long as we are able to identify some of the quantities that we have, then we are able to make use of the EMF equation. Right. So if we are given the EMF and the internal resistance, we are also able to find the total current. Right. Now, here is a practical example. Consider the circuit shown. Okay, the internals of the resistance of the battery cannot be ignored. So let's interpret that. It's a very important piece of information. We are told that we are not going to ignore the internal resistance of the battery. What does that tell us? It tells us that the internal resistance of the battery is not negligible. We are going to take into account the internal resistance of the battery. Very, very important. Right. So here is the circuit that is given. Right. If we can look at it, it says with the switch open, okay, you can realize that even in the given circuit, the switch is open, right? The reading on V1 is 9 volts, right? What is this reading of V1? With an open switch, what does V1 actually measure? V1 is equals to 9 volts. What does that tell us? It tells us that E is equals to what? A V1, which is equals to 9 volts, right? So with the switch open, the potential difference across the ends of the battery, it actually gives us the EMF reading. So V1 measures EMF with the switch open, right? Okay, now we are also told that when the switch is closed, the ammeter reads 0.4 amperes. So when we close the switch, we have got an ammeter reading of what? 0.4 amperes. Now we are supposed to calculate the internal resistance of the battery, right? Okay. Okay. Now, what are we saying? We are saying that the current that goes through the 5 ohm resistor, in this case, which is connected in parallel with the other 5 ohm resistor, is equals to what? 0.4 amperes. So if this is 0.4 amperes, what will be the current that goes through the other 5 ohm resistor? What is very, very important here is that the two resistors are actually connected in parallel. And these are identical in the sense that they've got the same amount of resistance. So whatever current goes to the 5 ohm, it will be the same amount of current that would go through the other 5 ohm. So current will be equally split. Here we've got another 0.4 amperes. So what is the total current in the circuit? We can choose to look at it that way. Or we can use the equation, right, to find R, okay, which is the total R. Now, if we are to say, okay, if 0.4 goes through, let's call this the 5 ohm, let's call it R2, and let's call this R3, let's call that R1, and let's call that R4. So the total current in the circuit, in this case, we realize that total current is equals to 0.4 times 2, which is 0.8 amperes. Right. But now let's go via the route of calculating using the EMF equation. Okay. We can find the total resistance. Okay. of the circuit, which is, first of all, we need to find the R parallel, okay, which is the 2. So R parallel in this case is equals to product over sum. Product is R2 multiplied by R3 divided by the sum R2 plus R3, right? So if you do your maths, that gives you 5 times 5, which is 25, divided by 10, okay, which is 2,5 ohms, right? 2,5 ohms, right? This is R parallel. So the total resistance in this case will give us what? 2,5, which is in series with the 6 ohms, which is in series with the 2 ohms, right? So the total resistance that we get here is going to be, what do we have? 6 plus 2, which is 8. 8 plus 2,5, which is 10.5 ohms. But actually, we want to appreciate that this is R external, which is 10.5 ohms, right? But we are interested in calculating the internal resistance, right? But now we have the total current in the circuit. We are able to do that, right? Okay, so if we go the route of saying E is equals to I, okay, R plus R, okay, we are able to say, okay, when that switch was, EMF is 9 volts. When the switch was open, okay, we know that the total current in the circuit, in this case, this is the current for the 5 ohms. So the total current, that's the catch, right? If 0,4 goes there, right, another 0,4, so we'll have 0,8, right? Then the total resistance, we've managed to calculate it as 10,5, right? Then we are able to get the small r, right? So what is our value there? We can quickly go to our calculator, but before we do that, we are able to say this is the same as 9 divided by 0,8, right? Minus 10,5, right? 10,5, this gives us our internal resistance. So we can go to our calculator and say, okay, this is 9 divided by 0,8, which is the total current in the circuit, right? This less 10.5. Okay, what does this give us? It gives us a value of 0.75. So our internal resistance of this circuit is equals to, just to confirm that value, 0.75, all right? 0.75 ohms. So this is a very small resistance that the battery actually has, right? So we're good with that, right? Now we have another circuit problem. In this case, we're also given the EMF of 12 volts and an internal resistance of 1,5. So what's different in this scenario, if we compare it to the earlier one? In the first case, we had to arrive to say, okay, we have the EMF, even though it was not given directly. We needed to appreciate that the switch is open, so the potential difference across the battery is actually the EMF reading. So in this case, we're given the EMF, okay? We are also given the internal resistance, right, which is 1,5. So we're saying E is equals to 12 volts in this circuit. Internal resistance is equals to 1,5 ohms, right? This is what is given, okay? Right, so they want us to determine the current through the 25 ohm resistor, right? So in other words, we are looking for current that goes through the 25 ohm resistor, right? Let me just correct that, okay? So we want the current that goes through the 25 ohm resistor. We also, if we look at the circuit, right, all the current passes through the 25 ohm resistor. So this is like the total current of the circuit, which is what we are looking for, all right? So that's our interpretation. So we want to determine that current, all right? Now, first of all, we need to look at the effective resistance of this parallel combination, which is actually in series with the 25. So again, we can use the formula, the R parallel is equals to, let's say this is R1, that is R2, and then that is R3, right? We can say product over sum, which is applicable only for 2 resistors, which is R2 multiplied by R3. divided by the sum of those, which is R2 plus R3. Okay, so if we say product there is 60 by 60, right? Divided by the sum, 60 by 60, which is actually 120. So what is our R parallel? Okay, our R parallel, we can simply obtain that 60 by 60. These are identical resistors once again, okay, because they've got the same resistance whose sum is 120 ohms, right? So that gives us 30, right? There's something very interesting. You'd realize that when we have two resistors connected in parallel, their effective or combined resistance is actually lesser than the smallest resistor. So the smallest resistor in this case is 60 ohms. So the effective resistance must be less than 60 ohms, okay? Now, which is 30 in this case, which is actually half of that. So this is 30 ohms. So total resistance, R in general, which is the total resistance in the external circuit, is equals to R parallel, right, plus R1, okay? R1, which is our 25 ohms. In this case, which is 30 plus 25, that gives us 55 ohms. Okay, so that's our total resistance. But remember, we want the current, right? Okay, so if that's the case, this is what we have. Okay, so if we want the current, we are saying this total resistance is 55 ohms. We've managed to obtain that. Okay, so the equation says E is equals to I, okay, which is the total current, external resistance, which is in series with the internal resistance of the battery. So we have all these values except for the current that goes through 25 ohms, which is the total current. Okay, so our E is 12. Right? We're looking for the current. What do we have there? We've got 55, okay, plus given the internal resistance, which is 1,5. Okay, right. Then if we are looking for I, in this case, our total current is going to be 12 divided by the sum of those 55 plus 1.5 is 56,5. Okay, then we can say then the current which goes through the 25 ohm resistor. If we go to the calculator, what does it give us? We have got 12, okay, divided by 56.5. Okay, this gives us a current of 0,21, right? The current is 0,21 ohms. Right, now this is we can say therefore this is the current that goes through 25 ohms, which is actually the total current in the circuit. Right, okay, so the value of current is 0,21 amperes. It should be to 2 decimal places unless or otherwise specified. So the current is 0,21 amperes. So this is the total current in the circuit, which is the same as the current that goes through the 25 ohm resistor, because that's what the question required of us. Right. So having said that, I think it's very important to say these are just examples that we've used, and with more and more practice you become very comfortable around working with circuit problems, and the attitude is that you always treat each scenario as unique. But as you do more and more practice, you get to realize, okay, there is something that's common about them, but each question must be treated, you know, as unique as possible. So these are some of the simple examples, but the idea is how you approach the circuit problems. Having said that, that's all the time we had for today. It's bye-bye for now.